In this example, we're looking at a pulley that's shown there in the figure. Let me scroll it down here. There are two cables. One cable which is attached to ground up here. It's wrapped around the outer radius of the pulley. It comes off or goes onto the pulley there at point C. There's a second cable that's wrapped around the inner radius of the pulley. It's got a free end here at A, and it comes off of the pulley here. Both cables are assumed to not slip on the pulley as things move. Someone is pulling upward on the end A of that cable coming off there on the right. We know the rate at which that person is pulling it up is 3 feet per second. And eventually what we want to do is use the instant center approach to come up with the velocity for this point B, which at this instant is directly above the center of the pulley O. So our first task here is to find the instant center, identify what the instant center is of the pulley. Well, the argument that I would make here is that every point on the cable over here on the left hand side, those velocity of those points is a zero. Okay, so as this cable then wraps around the pulley here on the outside, this point C is still a point of zero velocity. Once we drop below there and we look at the cable wrapped around here, these points do have non-zero velocities. But C, being that cable doesn't slip on a pulley, has to be the instant center for the pulley. That's a very key observation. Okay, so with that said, and knowing the velocity of A, that's the same velocity as all these points along here. And so if I call this point E, then the velocity of E is the same as the velocity of A. So we know velocity of E. We can also say that since C is the instant center, the velocity of E has to be equal to the distance between C and E. That distance is equal to R plus R times the omega for the pulley. Okay. So therefore, the omega of the pulley is equal to the velocity of E. That's the same thing as the velocity of A divided by R plus R. And with knowing that velocity of E is like this, we reason then that this pulley is rotating in a counterclockwise sense about C, like that. So this is the omega for the pulley based on knowing the velocity for A. Now let's come up here to point B. Well, B is on the same rigid body as C. So if I draw a line up here to B, we know velocity B has to be perpendicular to the line that connects B back to the instant center. So this velocity of B is like that. It's at a 45-degree angle. I guess I didn't draw that line right. Let me try doing a better job on drawing that line. C is actually down here. So I draw a line between C and B. Perpendicular to that is BB. And so this is at a 45. So the speed of B is equal to the distance between B and the instant center times omega p. The distance between B and C, that's going to be the square root of 2 times big R. Omega p we saw was VA divided by r plus r. So again, VB is perpendicular to the line that connects B back to C. So, what did we do? Well, we reasoned through where the instant center had to be, because that pulley has this cable over here on the left-hand side wrapped around the outer radius. If the pulley doesn't slip, then the velocity of the contact point C has to be the same as the velocity of the pulley or the cable that's hanging down, and that hanging down cable is stationary. So that's the argument we went through to reason out that the velocity of C is a zero. Once we had that, everything else falls into place. The speed of E, that's equal to the omega times the distance between E and C. E has the same velocity as A, and that's how we got this equation here. B, we go back from B to C, draw that line. Perpendicular to that line must be VB, and its speed must be the distance between B and C times the omega for the